Hello everyone, my name is Wang Zhendong. It's my honor to report our work on the second lead challenge, Track-3, Weakly Supervised Object Localization. My partner's name is Chen Zhenyuan, and our instructor is Professor Gong Chen. All of us are from Nanjing University of Science and Technology. Let's begin with our outline. The first one, I will briefly analyze the problem. And secondly, I will describe our model. And then I will show some our experiment or results. In the end, I want to talk about the future improvements of our model. Problem analysis. As we all know, weakly supervised object localization is to localize the objects in an image only with image level annotations. There have been a number of ongoing investigations regarding weakly supervised object localization, covering self-transfer learning-based, attention-based, multiple instance learning-based, and one of the most recognized approaches is class activation map-based method. We consider that only using image-level labels is too weak, so we try to utilize the information of raw image to promote the age and other details. So we designed a network composed of two autoencoder parts. Here is our model, our network. As we can see, we designed a network with two autoencoders. In the first part, the left part of this image, we train a classifier with global average pooling in the first encoder. Under the supervision of image level annotations, we weight and sum the convolutions to get class activation maps. Then we use binary images generated by class activation maps as pseudo pixel level annotations, followed by the first decoder. We use bilinear upsampling to get the binary image with the same size of raw image and calculate the loss in each convolution. In the second part, the right part of this image, we expect to recover the binary image to the raw image in order to get the refined binary image. The output binary image of first decoder is used as the input of second encoder. The binary image is compounded with the raw image and then divided into front and background. The front part and the background part are operated in different channels of layered independently and then fused as the final predictor image. We transfer front and background images in all layers into new binary images, which are used as pseudo annotations for the next iteration, and then we'll train the network iteratively. Here I want to talk about the detail how we transfer front and background images in all layers into new binary images. Firstly, we train transfer front and background images to binary images with a threshold, and then we add the front and background binary images together reversely, and we fuse the binary images of all layers so that we get the new binary images for the next iteration. Okay, let's talk about our loss function. Our loss function is composed of three parts. The first one is loss LK between binary image prediction and pseudo pixel level annotations. Second one is mean square loss of class prediction. The third one is cross entropy loss between the final output image and the raw image. I want to talk about the first one, LK, K is the number of layers, and this loss is composed of two parts. One is cross entropy loss, pixel level pseudo annotations (GRC), and network prediction (SRC). The other one is image structure information loss, which we can see in the picture. We can see above is LSSIM. This is our model. Okay, experimental results. Our model achieved 61% peak IOU in test datasets. Because of the wrong choice of one parameter of output image function, our peak threshold is only 7. Well, we corrected this mistake and improved the peak threshold obviously. Then we give some our results. Above output images show that our method works well on images with a single object or overlapping objects. The three images in left panel demonstrate that our model can localize the objects with a small, local, complex edge structure clearly. The three images in right panel show that our method is also applicable to the images containing multiple instances belonging to one category. Certainly, our method has some disadvantages. Here gives some our failure cases. We found that our method does not work so well on situations as shown above. One is with spatial strips like this, and the other is with some interfering information. Considering these flaws of our model, we want to take some future improvements. Firstly, we plan to bring the REST-to-net structure to downsampling layers, which can provide information of rich scales by integrating the channels. And as shown in the figure, in the right figure, these smaller filter groups are connected in a hierarchical residual-like style to increase the number of scales and the output features can represent. Secondly, we want to add strip pooling in our encoder-decoder model, as this strip pooling can help the network better exploit long-range dependencies. We use h times 1 and 1 times w strip pooling kernel, so that extend the result to h times w at the value at correspond position, followed by a sigmoid and then times raw data to get the output. We carried out some preliminary experiments. The results show that our improvements promote the effects on some challenging images. Okay, that's all. Thanks for listening.